Good morning, students. Let us finally conclude what is gravitational potential energy at a given position. Okay. Now, suppose I want to find out gravitational potential energy at a point P due to Earth of mass m. Then we calculate gravitational potential energy at this point P as work done by gravitational force in bringing that point mass from infinity to that particular point. Work done in bringing a point mass from infinity to the point under consideration is called as the gravitational potential energy at that position. Let us see how is it calculated. Work done by gravitational force in bringing or in displacing a point mass m from infinity, let us say it is somewhere here, from infinity the point mass is got from infinity. The point mass is got and displaced over here. It is being placed over here. So work done by gravitational force in displacing a point mass from infinity to the point under consideration. In the gravitational field. The gravitational field of the Earth is stored in it as gravitational potential energy. So let us calculate this as we have done earlier, same way. So it is calculated as work done from infinity to the point under consideration. From infinity to the point under consideration, that is at R. Point under consideration is at R from the center of the Earth. Let us say it is at the point P is at center. From the center it is at distance R from the center of the Earth. P is at point distance R from the center of the Earth. Then we take variable force into dr. Variable force into dr. So variable force, if we just denote it as GMEM upon R. So yesterday we have taken as small r only. Let us take small r square into dr. So this we have calculated already from infinity to the point of consideration r. So if you differentiate this, we get minus GMEM upon as integration of 1 upon r square dr from infinity to the point r. Same r is there. So if you integrate this becomes minus, yes. Now we can integrate. Integration of 1 by r square gives you minus 1 by r. Therefore, infinity to point P, the work done becomes minus GMEM into 1 upon r from infinity to the position r. You can take this position as different notation also, since r is the notation for the distance, so I have taken r itself. Therefore, it becomes minus GMEM upon. So upper limit is r only, so 1 upon r minus 1 upon infinity. Lower limit is infinity. So anything divided by infinity is 0. Therefore, you get minus GMEM m upon r minus or minus plus, and this becomes 0. So this is how we get the potential energy at a position r as equal to work done in bringing a point mass from infinity to the position as equal to minus GMEM upon r. That's how we get the result. Now, one more thing you please understand here, the potential energy at infinity. Potential energy at infinity, you see, when you put r equal to infinity here, it becomes 0. So, u at infinity is 0. So, this is the highest possible potential energy. Otherwise, at all the positions, the potential energy is negative. So, the potential energy, yesterday itself I have told you, potential energy of a body around the earth at any position is negative. It means that body is bound to the gravitational attractive force, gravitational attractive field, and it is not free to move away from the surface of the earth. It is under the gravitational attractive interaction. Whatever position you take away from the surface of the earth, that body is always attracted towards the center of the earth. So the gravitational force is attractive, therefore gravitational potential energy is also attractive potential energy. As a result, we get negative sign. The negative sign is to symbolize that the gravitational force involved is attractive force and the body is bound to the gravitational field of the earth. So with this knowledge, now we will define what is gravitational potential. Gravitational potential. Gravitational potential, again at any position r, it is denoted by V. It is denoted by V. Now here we have considered point mass m, which is being brought from infinity to the position T at a point at distance r from the center of the earth. If in case this point mass is of unit mass, suppose this point mass is 1 kg, what is that amount of work done in bringing this unit mass from infinity to this point under consideration? That is called as gravitational potential at that point. This is very simple. So, gravitational potential at any point is the gravitational potential energy per unit mass. Right? Because work done by the gravitational force in bringing a unit mass from infinity to the point under consideration is called as gravitational potential, which is also equal to gravitational potential energy per unit mass. So this I can write it as gravitational potential energy per unit mass. Per unit mass. So if you substitute this gravitational potential energy at this particular point, we got. So I will write V at position R. V is the notation for potential, gravitational potential. V at position R can be now written as U at position R, that is gravitational potential energy at position R divided by mass, because we want to calculate per unit mass. So divided by mass. So we get minus GMEM upon R whole divided by M. So M cancels. So you are left with minus GME upon R. So this becomes gravitational potential. So you can note down here the potential energy is inversely proportional to the distance between the mass and the center of the earth. In the same way, potential is also inversely proportional to the distance, not square of the distance. It is inversely proportional to distance. These two things you must remember. And therefore, we can define gravitational potential as See here, I can just write here itself gravitational potential as, I will just take out this energy, so I will make it a gravitational potential. Work done by gravitational force in bringing a unit mass, or you can write per unit mass, both are same. Unit mass from infinity to the point under consideration, that is called as gravitational potential. So gravitational potential, work done per unit mass. This is what we can call as V. So divided by mass. So if you divide it by mass everywhere, you will get mass getting cancelled. So there will not be mass here. So mass cancels. You are left with same thing without any mass. So this will not happen here. So we get the same result. So we carry out the same procedure and divide by mass, we get the gravitational potential at that point. So I have, from the same writer, I have defined what is gravitational potential. Gravitational potential is defined as work done by gravitational force of the earth or work done by gravity of the earth in bringing a unit mass from infinity to the point under consideration in the gravitational field. It is denoted as gravitational potential. You can write gravitational potential. At position R, right? M cancels. Once M cancels, you are left with only G. That's it. I think this is quite clear. Now, with this concepts in our mind, let us solve one or two simple problems. Okay? Okay, now read the problem. Find the potential energy of a system of 4 particles placed at the vertices of the square. This is the square of side L. Also obtain the potential at the center of the square. So, suppose the 4 point masses, 4 particles of same mass, 4 particles given here is 4 particles of same mass. You can take M. Find the potential energy of a system of 4 particles of same mass placed at the vertices of a square of side length L. Okay, first we will obtain this first part. Now, when the mass M is being brought, we will have to calculate total potential energy. So, with the meaning of potential energy, that is work required to be done in bringing the point mass from infinity to the point under consideration, right? Now, suppose this point mass M is there at infinity. This is the point mass at infinity. It is being brought from infinity and is being placed at this position. When this point mass M is being placed, assume that there are no other masses here. This space is empty. We are bringing one by one. We are bringing the point mass M here and another one here, and the fourth one here from infinity one by one. Not immediately we are bringing. So we will calculate the work done in bringing these point masses one by one from infinity to their respective positions at 1, 2, 3 and 4th of 4 vertices of the square, right? So let us first calculate work done in bringing the point mass from infinity at position 1. This is stored in it in the form of potential energy. When this point mass is being brought, there is nothing here. The space is totally empty. Think that there is no other, not even earth is present, nothing is present. So it is in the space. So definitely when no other field is there, when there is no other gravitational force is there, so work done becomes 0. So work done in bringing this point mass from infinity to the position 1. From infinity to the position 1 becomes 0. Call this equation number 1. Now already this point mass is being placed here. Now we are bringing second point mass from infinity. Second point mass from infinity. We are bringing it from infinity and we are placing it here. Now when we are going to place this point mass is under the gravitational interaction with the point mass 1, which is placed at 1. There will be gravitational attractive interaction. Therefore, there exists some gravitational attractive force. One has to do work against the force. So, I will write it as work done in bringing the second point mass from infinity to the position 2. It is calculated as, it is no more 0 here because there exists a gravitational force which is at a distance L. There is a gravitational force between this mass and this mass at a distance L between them. So I will write the gravitational potential energy directly using the equation which we have derived, minus G m into m, because both the masses are same, m into m, divided by the distance between them is L. So thus it becomes minus G m square upon L. Call this equation. Now two point masses are being placed. Now I am bringing the third point mass from another infinity, from here. This point mass is being brought from infinity to this position and it is being placed. Now when this is being placed, this is under interaction of two particles. One is the second particle at corner 2, which is at a distance L. Another one is at corner 1, which is at distance along the diagonal of this square. So this side length is L and so also this side length L, and there is a right angle between them since it is a square. Therefore we can find out what is this using Pythagoras Theorem. So L plus L, that is L square plus L square becomes 2L square. Square root of 2L square becomes the length of the diagonal. So it becomes L root 2. L square plus L square. So it becomes 2L square. So square root of 2L square becomes L root 2. So this length is L root 2 from here to here. So work has to be done against the interaction between these two particles. So work done in bringing the third mass from infinity to the position 3 is given by, look at this. First, I will write with respect to this particle, second particle, minus G m into m divided by the distance between them is L, minus, this is also minus G into m into m divided by L root 2. L root 2, because the distance between these two is L root 2, right? So thus we can simplify this as minus G m square upon L minus G m square upon L root 2. So this is the third one. Now we are bringing the fourth particle. As I said earlier, we are bringing the masses one by one. Now I am bringing fourth particle from infinity, another infinity from here and placing it here. Now this fourth mass, which is also same mass, is finding the interaction with mass at 1, interaction with mass at 2 with this distance, and interaction with mass at 3 with this distance L. So there are three terms here, right? So interaction is there due to mass m at position 1, mass m at position 2, mass m at position 3 with mass m at position 4. So now I am ready. Work done in bringing the fourth mass from infinity to the position 4, fourth corner is equal to 1 by 1 I will write. With respect to first particle, you can see here, with respect to first particle, it becomes minus g. I will write directly g m into m square divided by the distance between them is l. Then second one you see minus g m square divided by this is also going to be l root 2, the way we have modeled earlier. So this length of the diagonal is also going to be same, l root 2 minus due to the third particle which is at distance l, so it becomes minus g m square upon l. Right, now you can add all these, so it becomes minus gm square upon l minus gm square upon l becomes minus 2 gm square upon l minus gm square upon l root 2. So this becomes 4. Now total work done. Now we can calculate it as total work done in assembling these 4 point masses from infinity to the point under consideration. Points under consideration is stored in this system as potential energy of system of 4 point masses, right? Therefore, I will write here. Therefore, potential energy of the system of assembling 4 point masses at their respective positions is now I am writing it as U equal to sum of all these work done. So I write it as W infinity to 1 plus W infinity to 2 plus W infinity to 3 plus W infinity to 4. So this is how we get total potential energy. So from equation number 1 it is 0. From equation number 2 it is minus g m square upon l. So directly you can write minus g m square upon l. Then next third one minus g m square upon l minus g m square upon l minus g m square upon l root 2. And look here fourth one, this also we have to add fourth one. So that becomes minus 2 gm square upon l minus gm square upon l root 2. Now add all these 4 terms. When you add all these 4 terms, we get therefore total U is equal to 1, 2 plus 2 gm square upon l, gm square upon l, 2 gm square upon l. So it becomes 4 gm square upon l. So I write minus 4 gm square upon l. And here gm square upon l root 2, gm square upon l root 2. So it becomes minus 2 gm square upon l root 2. So this is how we can simplify now. So gm square upon l is common, right? Gm square upon l is common. If you take out gm square upon l, it becomes okay. You take out minus gm square upon l, then you are left with 4 plus 2 by root 2. So 2 by root 2, you see, 2 by root 2 is root 2. Root 2 is what? 1.41. So if you substitute 1.41 here, it becomes 4 plus 1.41. 4 plus 1.41 becomes 5.41. So it becomes minus 5.41 gm square upon L. This is the final result. So this is the total potential energy in assembling a system of 4 particles of same mass, placing them at the vertices of a square of length L. This is potential energy of assembling 4 point masses. The next one is, what is potential at this point center, at the center of this square? So center of the square, if you denote it as O, this center of the square, you see, is exactly at the same distance from all the corners. The center O is at the same distance from all the vertices. So it will be exactly L root 2 by 2. So from here also it is L root 2 by 2. From here also it is at L root 2 by 2. From here also it is at L root 2 by 2. And from here also it is L root 2 by 2. So gravitational potential at that point is defined as amount of work done, that is gravitational potential energy at that point per unit mass. Okay, let us calculate that. So assume that here you have kept 1 kg mass. M is equal to 1 kg mass, right? Then directly we can now write gravitational potential. That is second part. If you write it as V, gravitational potential at center of the square, that is O, is equal to, first start with already 4 masses are being kept here. So M into 1, it becomes 1. M into 1 becomes M minus G, M upon the distance between them is L root 2 by 2. L root 2 by 2. L root 2 by 2 becomes L root 2 by 2. So it becomes L root 2 by 2. So 2 comes to the numerator. 2 comes to the numerator. Similarly, for the second one, again minus G M upon L root 2 by 2. L root 2 by 2. By 2 means it goes to the numerator. So this is second one. Third one is the same thing. Minus 2 Gm upon L root 2. Fourth one also. Due to fourth one. Minus 2 Cm upon L root 2. So it's very easy to add now. Minus 2, minus 2, minus 2, minus 2, minus 8. So it becomes minus 8 times Gm upon L root 2. So this can be written as 4 into 2. So numerator becomes 4 into 2. So that we can cancel root 2 with 2. So it becomes minus 4 root 2 Gm upon L. Gm upon L. That is the final result. So that's how we calculate the potential at the center. Potential at the center of the given square. Okay. In the next video we will start with escape speed.